Okay, good afternoon, ladies and gentlemen. My name is Yangang Wang from Dynex Semiconductor. Okay. Okay, I think many of you know us. We are in Lincoln, East Midland. We're doing power semiconductor device and packaging and application. So today I will present here about our latest silicon carbide module development. Okay, I think it's an interesting topic. Warwick has talked, and ST also has presented something. So there are several sections here. I'm reporting automotive power module market and status, silicon carbide packaging challenges and solutions, and from us, our latest development on automotive silicon carbide module. And the last one, advanced technologies and new materials for customer and high-end applications. Okay, this figure, this picture is, I think, is very familiar for most of us. So IGBT and silicon carbide module is widely used in the EV traction inverter and DC to DC converter and onboard charger. So we can see here from low power and to the high power, from the power module to the discrete. We can see here. Yeah, this is a typical packaging here. We can see. Oh, yeah. It's a typical hybrid pack. Okay, this is a discrete module, discrete devices. So these figures are showing the EV market. So from 2019 to 2021, we can see here the worldwide EV, the green part is increasing significantly. This is we are very familiar. So, but the ICE is dropping year by year. So Asia, China is the main market at the moment for the BEV. Okay. The right-hand side, we can see here the silicon EV and the silicon carbide EV. The trend from 2022 to 2030, we can see here. After a couple of years, the silicon carbide car, we are talking about the main inverter application, will overtake the silicon in just maybe 5 to 6 years. We see here the red line, yeah. And the green line is dropping. That is because we mentioned that because of the 800 volts DC. We are seeing the high requirement and the market for the silicon carbide 1.2 kV power modules. So here is showing the market forecast. So maybe we know different companies, agencies can give different figures, but the latest figures I saw in recent years is okay. The EV main inverter will account for 60% of the 1.2 kV silicon carbide market. Okay, the EV is more than 60% on the main inverter. On the onboard charger is about 10% of the silicon carbide devices. Another main section for the silicon carbide application is solar panel. Okay, solar panel account for about 20% of the silicon carbide module power devices. Okay, this is just roughly ideas we're showing here from 2025 to 2050. The BEV penetration is increasing. Silicon carbide BEV is increasing. This is total silicon carbide module market for the inverter, and this is for the onboard charger. So latest figure showing that in 2025, silicon carbide module will be 3 billion. Okay, that is the forecast, 3 billion. Okay. In addition, the gallium nitride will be about 80 million in 2025. Okay. This I'm showing here about the worldwide suppliers for the power semiconductor modules for automotive. Okay. We see here from left to right is from European to Japan. You see here Japan, and this is showing here US, and in Asia, especially in China. Okay, we are CRRC here. Okay, part of Dynex is part of CRRC. Okay, we are doing automotive silicon module and automotive silicon carbide module, from the die to packaging and to application. So we can see here there's lots of big names from here. Infineon, Hitachi is here with ABB, okay, and Vicotech, Bosch, Semicon is all packaging. Infineon is IDM as well. So for USA, you know the big one, Korea Wolfspeed, and Microsemi is also the main players for this area. So for application, we know the 800 volts has some, I think, lots of advantages. We see from here we can see the charging time, efficiency, system cost, weight, charging time. This is the battery saving and the technology. We see 800 volts has majority of the advantages. So it's coming to a trend of in the next several years EV system. So 1.2 kV silicon carbide is the best choice for the 800 volts of the system. So 1.2 kV silicon carbide modules has seen very promising market. I mentioned 60% will go into the EV of the silicon carbide power module. This is showing some pictures. We just see from STM colleagues. So here is ST pack, and from top to the bottom, see here Wolfspeed, Infineon, from Rome, from the Hitachi ABB, and this is from Danfoss. That's all different packaging dimensions, outlines, different power levels, so that seems not uniform. So if we talk silicon carbide silicon module, we know this one. Okay, this is the most popular at the moment for the silicon 750 volts 1.2 kV IGBT module. This is the industry almost standard module. But for the silicon carbide, it's not yet at the stage. We don't have a uniform standard and very popular modules at the moment. So my next section about the silicon carbide packaging, the challenges and the solutions we are investigating. You see here, for packaging challenges, as various people talked, we see here low plastics, low thermal resistance, high operational junction temperature, advanced technology, high power density, and low volume, low weight, low cost, and standardization. Okay, so how to how to solve these challenges? What's the solutions for the module level? We see here. Okay, there's lots of from the structure, from the material, from the and to the technology. We see here, planar packaging can solve some problem. Embedded 3D packaging, so direct liquid cooling, double side cooling. This is for structure. Okay. For technology, silver sintering, copper sintering, transient liquid phasing, and for interconnection, for copper ribbon, aluminum ribbon, and for copper clip, for DLB, this is also talking about interconnection. Okay. For the material, we see here the epoxy compound, transfer molding, new materials, or direct cooling substrate. This is also a new technology, new material. IMB, integrated metal base plate. This is all the potential solutions for these challenges. We see here. Yeah? So from us, so currently we have a project to develop 1.2 kV silicon carbide module for automotive. How this is showing, okay, the aspect of our design aspect, electrical, thermal, mechanical reliability. This is the challenges, we just maybe is a summary of the last page, and what is our approaches, okay? For electrical, such as by optimizing the chip layout, busbar shape layout, interconnection, and substrate layout to reduce the parasitics, okay? By using advanced cooling concept, optimize the thermal path and the chip layout to address the thermal thermal challenges. By new material, new structure, new interconnection, and the busbar attachment, busbar pin shape and layout, we solve the mechanical challenges. For reliability, especially for automotive, so currently the new reliability standard, AQJ 324 from the ECPE, is well accepted for automotive qualification standard. So we need to consider the die attach, substrate attach, interconnection, terminal attach, encapsulation, and some other materials also related to the reliability. So this is a design aspect. Okay. Next one, what we are doing. So this project is from last year. Okay. This is the overall design to show here. This is our module overall dimensions, current voltage ratings, junction temperature. We are using overlapping busbar, laminated busbar, using auxiliary substrate to reduce the low inductance, to increase the higher current capability. We're using the silicon nitride in the module. This is showing inside of the module structure. There's at the moment is a half bridge, including 5 die per switch, including the bonding wire bonding for traditional packaging. This is the section to show here. So our key features, key parameters, you see here. This is using the same simulation softwares. We see here. This is our AC inductance. This is our resistance. We come to about 4 nanohenry and 0.27 to 0.48 milliohm from DC to AC. This is from DC to DC. Okay. Our junction to case thermal resistance 0.07 kilo per watt, K per watt. Okay. This is showing the voltage or electrical field distribution. This is showing our thermal simulation and the temperature distribution. Yeah. So we made our prototypes from last year. We do the electrical thermal test for double pulse, for SOA, for thermal resistance, everything. This is thermal resistance result. This is the inductance result. This is your double pulse test result. This is our module. Okay. So in addition to the traditional technologies, we're also doing developing advanced technology to increase the reliability. Okay, we can see here we do copper sintering. Okay, for the die attach, chip attached to substrate, and for the busbar attach, we tried the copper sintering. So copper sintering has the advantage for the cost is cheaper than the silver sintering, has the anti-migration property, and we can have currently some pressureless material for copper sintering. The process so is easier than pressured copper sintering. So this is our result about different attachment technologies. You see here from the epoxy, pressureless copper sintering, pressureless silver sintering, the SiC silver alloy. The lead silver alloy, and the TLPS, this is, and the pressure copper sintering. We see here the shear strengths. So in this project, we are using the pressureless copper sintering. The 42 to 43 megapascal is acceptable and strong enough. We show here is about the high temperature storage reliability result. Okay, and we see a bit degradation, but after 1,000 hours at 1750 degrees C, the reliability is still reasonable. So another technology for the chip attach we are developing is about the transient liquid phase soldering. Okay, this is showing our result. TLPS cost is low because the material is cheaper, using the copper tin. Okay, we are using the pressureless options, and the precise and the productivity is good. Okay, is high. So these are showing the IMC for the whole interface layer. Okay, from die to the copper DBC, we can form 20 to 40 micrometers IMC layers. So because the IMC layers copper tin is is about 460 degrees C for melting, so the reliability for thermal is very good. Yeah. This is our also this is a high temperature storage after and before. Okay. So the shear strength hasn't been changed significantly. Okay, next section for me is about our advanced technologies and the new materials for customer solution and high-end application solutions. Because we have make the design, make the initial prototypes, so we have this design precise material platform. So we can develop any special requirement for different applications. So I show here about our different versions, what we can do, such as for die attach, we can use copper sintering for different versions. For substrate attach, for soldering, transient liquid phase soldering. For bus bar attach, soldering, copper sintering. For the control and the drive pin, we use standard or press fit pin. We have this press fit pin technology at the moment. Substrate for silicon nitride or substrate free with pin fin substrate. Base plate, we can use AESIN, IMB integrated metal base plate or base plate free. For housing, plastic injection molding. For encapsulation, we can use traditional gel and or high temperature epoxy molding compound. So this is a transfer molding technology. So we do have this kind of technologies. Some of them are already being used, some of them are being development. So we suppose we can, according to different reliability, cost, performance requirement, we can select, we can choose, propose different options for different customer. Okay, my summary here, so automotive silicon carbide module, we know we are seeing high promising market opportunities, okay? But the qualification standard for automotive is high, is much higher than the industry, okay? Give us very big challenges, but we do see some potential solutions, and some of them are verified, okay? We have showing here 1.2 kV 500 automotive silicon carbide module, designs, simulation result, assembly process, and the test I have shown here, okay? So for high performance, high reliability, custom high-end silicon carbide module, we can develop according to customers' requirement based on the technology and the material we have already get. Yeah. Okay, that's all from me. Okay, thank you, everybody. Thank you, my colleague Paul Taylor, doctor, gave lots of suggestions for this presentation. Yeah. Thank you. Okay.